All right, well, good morning, everyone. We've got another day that we're going online. Today it's because of the tropical storm that's coming through, but I guess 2020 just continues to give us all new challenges in different ways each day. But a little bit of a different setup here today, so hopefully this comes out as good as we can get. But what we wanted to do today is hopefully finish up chapters 9 and the portion that deals with molecular orbital theory. Now, if you recall, on Friday, what we had discussed was this idea of hybridization. And we talked about getting paint and mixing blue and red paint and getting a different color out of it, right, purple. But that purple color has qualities of the blue and qualities of the red. And so that's what the color purple is, right? A mixture of the two there. And so that's the same idea that's happening when we deal with hybrid orbitals. We mix our S and we mix our P orbitals, and we get a new set that has qualities of both of the things that we put in there. So that's one important thing to recall, right? When we mix things together, we have the quality of everything that we mix together in there, okay? The other thing to remember is that as we add different orbitals to make our hybrids, we start to take on more of the qualities of whatever is in there in the highest percentage, okay? So again, back to the examples that we talked about, we said if we have 1 gallon of blue and 1 gallon of red, right, we have a 50-50 mix of blue and red. If we have 1 gallon of blue, right, and 2 gallons of red, then 66% of our mixture is red. And so the purple that we make is a little bit more reddish, okay? So if we take that idea back to orbitals, right, S and P make 2 sp orbitals, okay? And so we have, those are 50% qualities each of the S and the P. And as we move to sp2 and sp3, we have more of our P characteristic in there, okay? So that's our very brief summary of what we talked about. The other thing that we mentioned, just kind of how we represent this in the pictures and the diagrams that we use, right? And this is kind of the classic, well, I shouldn't say classic. This is the standard representation that that we typically deal with when dealing with orbitals, right? And so over on the left-hand side, we have some kind of energy scale. That's just for us to discuss increasing energy or which orbitals are at higher energy or not, right? Our 2s orbitals are at lower energy than our 2p. Might be a good idea to maybe follow up on that statement and ask why, right? Or if can you rationalize that? And that goes back to one of these other discussions that we had about how we construct the periodic table and how we fill in electrons into what orbitals and our quantum numbers, right? But what the theory of hybridization says is that if we take electrons that are in our S, we promote them, and then something magical happens wherein we can hybridize and make a new set of orbitals which have characteristics of our S and our P, right? So now if you pay very close attention here, and if you look at the notes or on the slides here, we notice that our hybrid sp orbitals are higher in energy than the S, but it's lower in energy than the P, right? So that's when we kind of talk about characteristics of both there, right? They're in between there. And we also notice that we have 2 unhybridized p orbitals that don't change energy, okay? If we don't do anything to the orbitals, they don't change energy. They stay where they began, right? We also talked about, or we started to get this idea of how the hybridization dictates the geometry, okay? And for each hybrid sp orbital, right, so we make 2 hybrid sp orbitals, they are 180 degrees apart. So again, if you go back to this idea of why geometries exist to begin with, or why they're formed, we said that, according to Vesper theory, that electron pairs and lone pairs want to spread out as far as possible. So if you have 2 things and you want to spread out as far as possible, 180 degrees is the furthest we can get, right? And so we're going to build on this idea a little bit later when I kind of give you guys the checklist or the procedure to go through this, okay? But the point to think about at the moment is that the hybridization is inherently linked to the geometry of the molecules themselves, okay? All right, so moving on from sp to sp2, now we make some paint again, right? We have an S and take 2 of our p orbitals. Again, it's arbitrary. I'm just picking x and y. It doesn't really matter. We're just saying 2 of our p orbitals come together. But that means we have 1 unhybridized p orbital that remains. These are going to be important. We'll talk about why in just a minute. But we mix these 3 orbitals come together, so we have 3 orbitals that better come out of it, okay? And so we have 3 sp2 orbitals that get formed. If we have 3 things around a central atom, 120 degrees apart is the maximum that we can spread them, okay? And so hopefully at this point you guys are familiar enough with your geometries that when you see 3 things 120 degrees apart, you're thinking trigonal planar, okay? And so that's exactly what happens. We have 3 sp2 hybrid orbitals in the plane, right, in one plane. Obviously, if we mix the x and the y, then we're going to be dealing with the xy plane, okay? There is a reason why I didn't use a z orbital, and I guess to keep things a little bit simple, we'll just say it's for convention's sake, right? That's not too important, but there is a reason why we typically deal with the x and the y orbital and not the z orbital, but a little bit of a discussion for a different time also. All right. So if we take the, let's say the cartoon representation here, right, and we take it again to this standard representation of orbitals. Remember, each of these boxes just represents an orbital, okay? So now we have our S and our P. We do our promotion, we hybridize to make 3 sp2 orbitals, and we have 1 unhybridized orbital left. Again, our hybrid orbitals are somewhere in between in energy here, okay? And the important part to recognize again is we have 3 orbitals that are hybridized and they're 120 degrees apart. I think you guys can start to see where this stuff starts to come together here, okay? One last one, but with the exact same idea. We mix everything together. We have 4 orbitals that come out and they're 109.5 degrees apart. And so they have a tetrahedral geometry to them, right? We have the same representation here, okay? And we start to see how we can build these things together, right? Mix everything together, and then we can start to assign electrons into these hybrid orbitals to maybe start to dictate how things can form themselves, okay? Although I have a little bit of a problem with how the book represents this, but I'll show you guys how we're gonna do it here in just a minute, right? But anyway, the point is, once we have our hybrid orbitals, we can start to look at which orbitals want to form another bond, right? And which ones are already filled and going to form lone pairs. That's what they're trying to show here, okay? So remember, we're dealing with atomic orbitals at the moment, right? When we talk about sp3, we're hybridizing things on an atom themselves. And if you already have 2 lone pairs living in one of these orbitals, then, you know, it's not going to be able to bond with anything in the manner that we're thinking of with a sigma bond, right? Now, we can talk about Lewis acids and Lewis bases, and we can deal with that a little bit more later on, right? But what we want to see here at the moment is, right, if we have 2 vacancies in our hybrid orbitals, then we can predict that there should be 2 bonds that go into, or excuse me, 2 bonds that get formed with that specific atom, right? So remember, we're dealing with orbitals on a specific atom still. And remember, the whole point of doing hybridization, or one of the ideas that come out of hybridization theory, is where are the lone pairs and how do we know how many bonds and that kind of stuff gets made, okay? And we can see the same thing applies to ammonia, right? We end up hybridizing to make an sp3. We have 1 filled orbital already, and then we have 3 vacancies in our apartments there, our orbitals, and so we predict that there would be 3 bonds that get formed with ammonia, okay? Okay, so now let's add in a little bit of terminology here. So if you recall, I believe it was on Friday also, where we talked about how does a bond actually form. And the simplified idea is that for a bond to form, we have to have direct overlap of the orbitals, okay? We're talking about a head-on collision. Right, so when 2 atoms come together, they have to hit in a manner where the orbitals overlap in a maximum fashion, okay? So think of a direct head-on collision with your car, right? So that's kind of what's going on with an orbital here, okay? Now, there are two types of bonds that we're going to deal with. And in reality, those two types of bonds account for, I would venture to say, 99+% of the bonds that we see in all molecules, no matter what level of chemistry you're at, okay? So there's two types of bonds that we got to deal with. There's a sigma bond, right? There's a sigma bond, and then we'll talk about a pi bond, okay? Here's the distinction between sigma and pi. Whenever you form a bond between any atom, okay, the first bond that's formed is always a sigma bond. A sigma bond is a direct head-to-head overlap of any orbital, okay? That's all there is. So if you go back and you take a look at every molecule that you've ever drawn as a Lewis structure or in its molecular geometric form, right? Every single line that you've drawn in between two atoms represents a sigma bond. There's always a sigma bond for every type of bond that we represent, okay? It is the first bond that's formed. They tend to be the strongest bonds, okay? And their electron density lies in between the atoms themselves, okay? So a sigma bond is in between two atoms. So if we think about this for just a second, right? If we go back to our obscure example of water that we love to draw over and over and over again here. Oops, let me just change colors here real quick. All right, let's do blue. So in our example of water, okay, that. In blue, right, our single bonds are our sigma bonds. Okay, that's all we're talking about. And if we think about it, right, the reason why we draw this line in between the two atoms is for us to see which things are connected, but it also tells us that the electron density for a sigma bond is in between those two atoms themselves, right? That's how they overlap, that's how they share, that's how the orbitals are going to be interacting in that way, okay? So they're in between the atoms. Now, the reason why I'm stressing this is because we're going to learn a different type of bond, and their electron density is going to exist in a different place, okay? So, back to the point here. So, be careful, okay? In some books and in some videos and in some resources, they say single bonds are sigma bonds, and that's kind of just where they leave it. They're not wrong with that. But the point that I want you guys to think about is that the first bond that gets formed is a sigma bond. Anything else after that first bond is going to be a pi bond, and we'll talk about those in just a second, okay? But every place that you see a bond has one sigma bond, and only one. So that's the other point. One of the questions I'm going to ask you is count your sigma bonds, count your pi bonds, and so the sigma bonds are easy. You just look for wherever there's a bond and you count one, because that's the maximum number of sigma bonds that can be in between a single set of atoms, okay? So this looks like, you know, a nightmare, a bunch of balloon, you know, kind of balloon representations here, but they're just talking about how the orbitals overlap. We're considering the orbitals here around carbon to be the hybrid orbitals, and then hydrogen is interacting with those with its 1s orbitals, okay? And then we end up forming 4 sigma bonds like we talked about here in methane, okay? All right, now how do we deal with extended octets? How do we deal with things beyond tetrahedral? The short answer is, sorry, I'm in a new room and I've got cabling a little bit different. This might be fun, right? You might end up seeing me trip over everything, and that'll be recorded. But we hopefully won't get there. But anyway, back to the point. How do we deal with things beyond tetrahedral? Because remember, once we've gotten to tetrahedral, for every period that we have 1s and 3p orbitals. So the maximum we can do is make our sp3. To get beyond that, we're going to have to mix in d orbitals. And so remember, for each orbital you put in, you can make another bond out of it. All right, so what do I mean by that? So if we're going back to sp3, we put in 1s orbital and 3p orbitals. So we can make a maximum of 4 bonds, okay? If I add in a d orbital, now I can make 5 bonds, and if I add in 2 d orbitals, I can make 6. right? So that's all we're talking about here with trigonal bipyramidal and octahedral, okay? So as we get into these extended octets, we have to mix in the appropriate amount of d orbitals with that. We do have unhybridized d orbitals, and if we were doing a advanced chemistry course, then we would go and talk a little bit about what the implications of that are, right? But anyway, so if you see these extended octets, you call them DSP3. If you call them SP3D, that's fine too. At D2 SP3 or SP3 D2, just fine also. It doesn't really matter, right? Remember, when you name a hybrid orbital, you basically just call it what the orbitals that you put in are, right? Just like we call SP3 to represent our 1s and our 3p orbitals. Okay. So just a little bit of clarification here then. If you recall, on Friday, I kind of told you that hybridization is a little bit of hand waving. I'm not going to spend too much time on this. I don't need you guys to necessarily, I don't know what's the word I want to use here, not memorize, but I put this here for completion's sake. Let me put it that way. Remember, one of the things that I told you, or one of my statements, was that Lewis structures are a lie. And then molecular geometries are a lie, right? And then I could even continue that and say that hybridization is a lie. What I really mean is this. Lewis structures are an approximation, okay? Molecular geometries are an approximation. Hybridization theory is an approximation. All we're doing is taking an infinitely complex arrangement of atoms and electrons and trying to simplify it in such a way that we can do it within, 30 seconds of seeing what a molecule is, okay? We are taking shortcuts. Now, these shortcuts are actually really darn good, okay? They represent what the molecules look like. They tell us where the lone pairs are. We can predict things like formal charge, and we have all this very important information that come out of them, but they are still an approximation, and they miss kind of the reality of things. And so quantum mechanics, which is let's say a more advanced general chemistry branch, okay, physical chemistry is what the course would be when we talk about quantum mechanics. It would tell us that hybridization theory is not exactly true. And I agree with that, right? And it's very demonstrable that hybridization theory fails in some ways. But it's also extremely true that hybridization theory helps us simplify this manner in a way that we don't have to have a computer or a calculator with us to tell us what the geometry is and the energies and how things line up, okay? We can do more advanced math to get to the exact representation of where the electrons are and the atoms and all these kind of things. And that's fine, that's great, but you don't need to do that every time, okay? You don't need to do that every time, right? We can take some approximations and get a lot of information from let's say a 30-second calculation and a 30-second analysis, right? If you want to spend days calculating the exact answer, that's good and that's useful, right? And that's part of the research that I do also, right? But that has its time and its place. And right now we're learning the basics, and those basics are very important, okay? So as much as I joke with you guys about, oh, this is all a lie, this is all wrong, that's true, but it's a good, useful tool, right? I wouldn't teach it to you guys if it wasn't useful, and it wouldn't be in the books if it wasn't useful, okay? All right. So now that we understand about sigma bonds, right? Sigma bonds being the head-to-head overlap, a pi bond is a side-to-side overlap of orbitals. You're like, oh my goodness, what does he mean with that? Well, I'll try and draw it for you guys here in a second. But before we get to me drawing, those are the two types of bonds that we need to deal with. A sigma bond is the first bond that gets formed between any atoms. Any bond in addition to a sigma bond is considered a pi. So for instance, if we go to our buddy ethylene here, right, C2H4, okay, each of the hydrogens, right, each of the carbon-hydrogen bonds is a sigma bond, okay? The bond in between the carbons as a Lewis structure we would draw as a double bond. That's fine, that's good, that's correct. A double bond is a combination of one sigma and one pi. That's what we need to start to recognize, okay? And you're like, okay, double bond, one sigma, one pi, got it. Why? Well, it goes back to this idea here. So if we go back and take a look at our buddy carbon here, okay? So let me just zoom in for a second. So if we're taking a look at this carbon, and let's use green here. That carbon has 1, 2, 3 groups around it. Okay, so that carbon has 3 groups around it. At this point, hopefully you guys can tell that this is a trigonal planar geometry, right? If we have one central atom with 3 things around it, trigonal planar, 120-degree bond angles, all these kind of things, okay? If you have a trigonal planar geometry, you have to be sp2 hybridized. You're like, okay, that makes sense. I remember that when I mix an s into p, I make 3 orbitals out of it, and 3 orbitals correspond to 3 bonds. Perfect. But remember that if I make an sp2 orbital, I have one unhybridized p orbital. Actually, let me do this in blue here, right? I have one unhybridized p orbital. That unhybridized p orbital forms our pi bond, okay? For every unhybridized p orbital, you can form a pi bond. You don't have to, but you can, okay? So, if we want to think about it, unhybridized p orbitals make pi bonds. And pi bonds are formed by the overlap, by the sideways overlap of unhybridized p orbitals. So here is my carbon atom, right? Let's just represent it as a sphere, right? Here's my other carbon atom that's represented as a sphere, right? So I'm just looking at those 2 right there. My unhybridized p orbitals are going to align in such a way like this, okay? And if you imagine me bringing these 2 atoms together in a sideways manner, the sideways overlap is going to happen between these 2 lobes of our orbitals there. And you're like, okay, you believe me, and there's pictures in the book, and the pictures are slightly better than my drawings, right? Okay, but right, we're just bringing this sideways overlap together of these 2 orbitals. What implications does this have? Well, so let's think about this for just a second here, okay? So let's pretend that we bring these 2 atoms together and they form a pi bond, right? So we overlap this stuff sideways and we make a pi bond. So when we do that, okay, a pi bond has its electron density above and below the plane of the atoms, okay? So you can think of them kind of like the hamburger buns on a hamburger, okay? The patty's in the middle and you have the 2 sandwich components above and below that. That's exactly what a pi bond is, okay? Remember, right, when you make a bond, right, when you mix 2 orbitals, whether to make a sigma or a pi or a hybrid, whatever it is, when you mix 2 orbitals, when you mix 2 things, the new orbital, the new thing is has qualities of everything that you mix into it, okay? So our unhybridized p orbitals have density above and below the plane of the sigma bond, is what it is, okay? So just like hamburger buns, that's what we want to think about there. Got it? So those can only happen when we have unhybridized p orbitals available. So you're not going to see double bonds form in tetrahedral sp3 hybridized geometries, okay? We can see them when we have some of these violations of the octet rule, right? But for sp3 hybridized things that follow the octet rule, we can't see a pi bond form there, okay? There's no unhybridized p orbitals to deal with. All right, so let's tie all this together. So typical question is, what's the hybridization of this molecule? Give me the hybridized geometry, or excuse me, give me the hybridized orbitals like sp, sp2, sp3, that kind of thing, right? How do we do all that? Again, at the beginning, you have to draw the Lewis structure, okay? Once you draw the Lewis structure, then you draw the electron pair geometry, and you identify that. So, as I said back at the beginning of this portion, we're just continuing on from the previous chapter. We learned how to draw a Lewis structure, then we learned all about our geometries and electron pair and molecular geometries, and then we learned about polarization, all this. Okay, I got that, right? So now we're just adding something after we have the geometry, after we get the geometry, okay? We pick the hybridization scheme that matches the electron group, okay? And then we can sketch the orbitals and we can label the sigma and the pi bonds, okay? But this is the order of stuff. You have to draw your Lewis structure, you have to draw the geometry, then you can pick the hybridization scheme, and then you can draw the orbitals, or you can label the sigma and the pi bonds, okay? So let me back up here for a second. I want to find a previous slide in my notes. There it is, okay. So if you go back in your notes to this, this is, what is it, slide 38 is what it is, okay? And I said that this was probably gonna be one of your most important slides, okay? So remember, over here on the left-hand side, there's our electron pair geometries, and now right next to it, you guys can recognize the hybrid orbital sets, okay? And this is the point that I want to tell you. You have to be able to identify your electron pair geometry, then you can identify your hybridization. Or if you can identify your hybridization, you can identify your electron pair geometry. Remember, your hybridization tells us how many total things can we fit around a central atom, whether they are lone pairs or bonds, okay? So either one of these things kind of tell us the same bit of information, all right? It's typically easier for me to identify the geometry and then talk about my hybridization after that, all right? But we can see that these are inherently linked together. So that's the point that I wanted to go back to. If I know one, I can know the other. That's all that it comes down to, okay? All right, so back to it. Let's see, we were here, right? Cool. Okay. So here's kind of a quick summary of everything that we talked about, right? Just one of my typical summary slides that I throw in for you guys. Valence atomic orbitals, right, are where we have our valence electrons make atomic orbitals. They make MOs. The MOs can extend over an entire molecule. We haven't talked about this part too much. I'll show you guys a couple slides later on. The number of atomic orbitals equals the number of MOs, molecular orbitals formed. Garbage in, garbage out, right? 4 orbitals in, 4 orbitals out, okay? The valence electrons fill the molecular orbitals following the same principles that we've talked about before, okay? Whenever we're dealing with orbitals, the rules are the same. We can only fit 2 electrons. One has to spin up, one has to spin down. That's all it is. All right. So what's the point of this? What's the benefit? What does it do? Right? So really, molecular orbital theory tells us exactly the state of the electrons. Okay? It gives us a better representation of the state of the electrons. For instance, if we draw the Lewis structure for oxygen, O2, we have bonding pairs, we have lone pairs, and we think that everything is paired up. In reality, it's not. And we can do experiments to test this. And actually, the experiments are not that complex. All you got to do is get liquid oxygen, and you can actually trap liquid oxygen between magnets. Super cool, right? But that's just what we're talking about, diamagnetic versus paramagnetic, okay? So if everything was paired, oxygen shouldn't react with the magnets. But we can show that, and you can even look it up on YouTube if you wanted to, right? But experimentally, it shows that oxygen has these unpaired electrons. And MO theory tells us why, or we can exactly see why. But before we get to that, I have to show you how we can address this first, okay? All right, so here is the simplified representation of things, all right? So limitations. What we're gonna do for this class is only deal with diatomic molecular orbitals, okay? So the maximum I can ask you is when two things come together. That's it, okay? As soon as we go beyond this, it gets complex very quickly. The ideas are all the same, but we have to know a different theory to approach something else other than diatomics, okay? So that's for a different course. If you guys want to come take my bio-inorganic course, then we'll talk about that there, and we'll do this visually without as much math as you guys might expect, okay? Anyway, so molecular orbitals are produced from combining atomic orbitals. Fine, you guys got that, right? So what happens is this: if I mix two atomic orbitals, whether they're hybrid or unhybridized orbitals, okay? If I mix two orbitals together, I expect to get two orbitals out. Depending on how those orbitals are mixed, whether they're head-on or side-on, I either make sigma or pi bonds, okay? Now, if we're dealing with simple s orbitals, then we can only make sigma bonds. There is no, a sphere, an s orbital doesn't have a side, right? So we can't hit something sideways with a sphere, got it, right? So if I mix 1s orbitals, I get a sigma 1s orbital out. Atomic orbital, molecular orbitals. And these are the diagrams that you'll expect to see. So when I use the word MO diagram, I'm talking about this kind of representation here. The lines represent the orbitals. On the outsides are the atomic orbitals. On the insides, in between, are the molecular orbitals, okay? The star represents an anti-bonding orbital, okay? And an anti-bonding orbital, for our purposes, is exactly what it's saying, okay? It's the opposite of a bonding orbital, okay? You guys got that? Now, how can we visualize this here, right? So there are two orbitals, or atomic orbitals, that mix together to make molecular orbitals here, all right? What we're going to do is construct a slightly more complex version of this, and then we're going to see how we can use it to predict things like why do noble gases not form diatomics, right? Why do diatomics form these kind of things, okay? All right, so now we take our simplest example of our molecular orbital diagram, okay? For hydrogen, we have our 1s orbitals on the outside. We can only make two orbitals on the inside. For H2, all we have are two electrons, okay? And our two electrons get filled into the lowest orbital. So whenever you guys fill in any orbitals, whether they're atomic or molecular, okay, you always start from the bottom and work your way up. 2 electrons per orbital, and we just keep going with life, is what it is, okay? Helium has 4 total electrons, so we fill in 2 in our sigma bonding, so we make a bond, and then we fill in the other 2 in our sigma star, our anti-bonding. So we break that bond, okay? So this is the reason why helium doesn't form bonds with itself, because we have to deal with all 4 of those. If we make some kind of diatomic helium species, there is no gain in energy for our molecule. It makes a bond, which is good, but the other 2 orbitals go into the anti-bonding, which essentially breaks that bond apart. So what's the point? Why is it going to do something, right? So there's no net gain in energy here, so it doesn't form any bonds, okay? What we call, or what we refer to as the bond order, okay? And the bond order, you can basically think of whether we have 1, 2, or 3, or 4, or how many bonds there might be. We take our bonding electrons, anti-bonding electrons, right? Bonding minus anti-bonding, and divide by 2, right? We divide by 2 because it takes 2 electrons to make a bond. Okay, so for H2, this guy over here, we have 2 electrons in our bonding. We don't have any in our anti-bonding. We did 2 divided by 1/2, or excuse me, 2 times 1/2 is 1 bond there, okay? Typical question that I would ask you, what is the bond order for? And then you guys would, that's me expecting you guys to fill in one of these diagrams and just executing this, math right here. bonding minus anti-bonding, divide by 2, okay? All right, here's a different representation of different orbitals that we can make. Sorry, I find myself, I talk a lot more when I do one of these videos, and so I have to grab a quick drink of water there. But anyway, we can make sigma bonds from our p orbitals. Okay, again, we're just saying if there's a head-on collision, right? So if we head-on collision between these two between these two lobes, we make a bonding and an anti-bonding set. And if we make the side-on, here we have our pi bond and our pi anti-bonding, okay? All orbitals work the same way. Head-on sigma, side-on pi. If you make a sigma, if you make a bonding, you make an anti-bonding. If you make a pi bonding, you make a pi anti-bonding, right? It's just garbage in, garbage out, right? You have to maintain this balance, right? We've talked about this quite a bit. What you put in is what you get out. 2 orbitals in, 2 orbitals out. 2 orbitals in, 2 orbitals out. That's all it comes down to, all right? Now, what happens is we will get degenerate orbital sets, okay? And so what we talk about here is, when we use the word degenerate, we're just talking about orbitals that are at the same energy level, okay? So, don't worry, this should become a little bit clearer here in just a second. All right, so here is normally where I'd stop with you guys, and we'd work through a couple of examples. I'd walk through this with you guys and say some things. So if you guys kind of zoned out for the last couple minutes, come on back and let's see what we can start, if we can put all these ideas together, okay? So first of all, let's zoom in here at the bottom. So this is a typical MO diagram that you guys will be given, right? This looks like a diagram that's on the equation sheet that I give everyone for exams, right? So let's look at this first here, okay? So this is the tool that we need to answer these questions. I don't expect you guys to memorize this, although in reality it's not too challenging, right? It's new, right? And it's different, and I know, you guys are like, what in the world is this guy talking about, right? But if you take a look at this and you just get comfortable, you have to work some problems, right? Once you work out problems, you're like, oh, it's not that bad, right? And it's not, right? But it takes some practice, because this is not something that you guys have talked about before, okay? So let's take a look at what's going on here, right? So we have s orbitals down here at the bottom. Look, we have an energy scale here, right? So low energy at the bottom, higher energy at the top, okay? That's important because that's why and how we're going to fill in our electrons. You always fill in electrons from the bottom to the top, okay? S orbitals here, you mix an S and an S, and you make a sigma 2s and a sigma star 2s, okay? One of the assumptions that we make is that our s orbitals are only going to interact with themselves. We'll leave it at that for now, okay? We move up, we have our 3p orbitals. Whenever we mix our 3p orbitals, we make a sigma star, we make a sigma bonding, and we have the corresponding sigma star orbital up there at the top. One sigma bonding combination, one sigma anti-bonding, 2 pi bonding combinations, 2 pi star combinations there, 2 pi anti-bonding. That's all it is, okay? This portion here in the middle, the molecular orbitals, okay, that's the portion that we need to use to answer our question, okay? So let's answer a question then. Let's say that we have oxygen, O2. What is the MO diagram for O2? So each side represents one of the oxygens, right? Our atomic orbitals here, okay? So each side represents oxygen. How many valence electrons does oxygen have, right? Well, the answer is 6, right? So we can fill in 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay? So you fill in your valence electrons on the sides there, and then you just come in and you use your valence electrons to fill in your molecular orbitals, okay? So let's do that. We have a total of, excuse me, let me back up for just a second, right? So we have a total of 12 electrons to deal with, 12 in, 12 out. So let's do it. 1, 2, 3, 4. Okay? 5, 6. Now watch. 7, 8. Let's pause for just a second. Why did I fill in electrons like this? Well, take a look. These pi bonds here are degenerate of equal energy. Whenever you fill in electrons at orbitals that are of equal energy, you always fill across before you come back in and pair up. Okay? So what are we at? 2, 4, 6, 8, 9, 10, 11, 12. Okay? This is the MO diagram for oxygen. Okay? So what information can we get out of this? Well, a couple of important questions would be, or one important question is, what's the bond order for O2? Now, if we draw the Lewis structure for O2, right, we would get this. Okay. So let's see if our molecular orbital, let's see if our MO theory matches our Lewis structure theory here, okay? So let's see what's happening. So remember, it's bonding minus anti-bonding divided by 2. Let me change colors. I'll go to green, and I'm going to circle my bonding combinations. So bonding, bonding, bonding right there. How do I know that those are bonding? Well, there's no star next to them, okay? Remember, the stars are the anti-bonding. Got it? So we have a total of 8 electrons that are bonding. Okay. Let's see what color I can use. Red. Anti-bonding, anti-bonding. So minus 4. Okay. Divided by 2 equals 2. So bond order of 2. That's all there is to it, okay? Now, follow-up question that's a little bit more in-depth. So the bond order of 2 just tells us that there are 2 bonds. You're like, yeah. But you notice I didn't necessarily say that they're 1 sigma and 1 pi, okay? Now, within the limitations that we're dealing with, that might be self-evident, but back up for just a second, right? So let's take a look at what our diagram actually tells us here. So let me erase this just for clarity, okay? All right. So take a look. Down here at the bottom, this sigma, right, this sigma bond is canceled out by this sigma antibond, right? So you make a bond, but you immediately break that by populating the antibonding orbital. We move up in energy. This sigma here, right, is not canceled out by the sigma star. So we make a sigma bond in our O2 molecule. Well, that makes sense. For any molecule to form, we have to form a sigma bond first, okay? So there's sigma here. We move up. Our diagram tells us that we make 2 pi bonds. 2 electrons in 2 pi orbitals tells us that 2 pi bonds are formed. So we would expect to see 3 total bonds, 1 sigma and 2 pi. But we move up and we see there's 2 electrons in the anti-bonding orbital. And so it works like this, okay? To change colors again for just a second. These 2 red electrons here, okay, essentially cancel out one of these bonds that we have here. Got it? So 2 electrons there basically cancel out one of our bonds. And so all we're left with is a sigma and a pi. So we have 1 sigma and a 1 pi bond, which is equal to a bond order of 2, and a sigma plus a pi is a double bond, okay? A sigma and a pi is a double bond. That went fast, okay? So if you want to back it up for a minute or so here and go back and walk through that, all I'm doing is assessing where the electrons are in the orbitals themselves, okay? All right. Now, what would be good, if you guys see that I kind of gave you guys a big list of diatomics here. Start at the top, work your way through the exact same thing that I did here, okay? Fill in your electrons into your MO diagram, check your bond order, check whether they're sigma or pi, right? Draw your Lewis structure. Does the Lewis structure correlate with this? All these kind of things that go into it, all right? It'd be good practice for you guys to do that. You have to practice this. You will see one of these questions on the exam, okay? So you have to get comfortable with doing this. I know it might be difficult out there. Stop, watch this video again, or read the book, or find a different video, whatever it might be, but you guys have to get comfortable doing this, okay? It's an extremely important concept. All right. Okay, and so kind of here's more of the answers as you guys go through and work through this stuff here, right? I kind of help show you guys the answers and talk about how strong the bond is versus whether they exist at all. If you notice right here with N2, we have a bond enthalpy of close to 1,000, right? And you'll notice that that correlates with a bond order of 3. Remember, we said that the shorter the bonds, the stronger they are, and so we can correlate that to the higher the bond order, right? The higher the more energy it takes to break that bond, okay? All right. Now we can get into some strange examples here. What if we have certain ionic diatomics? Okay. These are approached in the same way. So He2 with a 1+ charge. So I smash 2 helium atoms together and one of the electrons get ejected. If I ask you guys to draw the MO diagram for this, right, we just have our 1s and our 1s. A total of 3 electrons get filled in, right? And so I can ask you what the bond order is here. So bond order is our bonding, okay, minus our anti-bonding, divided by 2. So we have 2 bonding minus 1 anti-bonding divided by 2, right, equals 0.5. And that's a perfectly acceptable answer. We have half of a bond. So a bond order of 0.5. Now, how do we visually think about this? I don't know. I don't have a great answer for you either, right? And that's one of the benefits of MO theory here. It's hard, I mean, how do you draw half of a bond, right? Do you bond and then stop halfway, this kind of idea. And that's not the important part. The important part is that this would actually predict that this is somewhat stable, because we basically form part of a bond, and any bond that you form is a stabilizing influence on the molecule itself. That's why bonds form to begin with, right? Because it's lower energy, and we talked about atoms being lazy, going to lower energy, all these kind of things. So this actually says that He2 would be somewhat stable, right? And I think there's experimental evidence that shows this, right? We can trap an He2 plus in certain systems and all these kind of things. Now, I'm not talking about stable as in you can put it into a jar and seal it up, right? But we've actually seen this thing form, and that kind of stability, right? The fleeting stability that gets imparted by half of a bond order, right? That kind of thing. All right. Now, let me tell you guys a little bit of a more complex idea, right? So these kind of balloon-looking things over here are the starting MO diagrams on more complex molecules. Now, it doesn't really matter why are they red, why are they green, why are they in this shape, why are they, these alternate, like all that stuff is fantastic questions. I'm going to be happy to answer that for you, but it's a little bit outside the scope of what we need to talk about here. Here's the point that I want to tell you. So if you take a look at this diagram here, so these are orbitals that exist on all 6 of these atoms at the same time. 2 electrons live in this orbital. So what I'm telling you is that 2 electrons live somewhere spread out over all 6 of these atoms. that is one of the consequences of MO diagrams, or of molecular orbital theory. Electrons don't really live in between two atoms themselves. They're spread out over a larger region, okay? So even in this diagram here, we could see two electrons living, kind of hopping in between all those individual components. And same thing with this one here, right? The point is this. So when you guys get to one of your advanced chemistry classes, you'll talk about this more, and it'll become a little bit more evident about why this is the case. But why we stick to only diatomics is because as soon as we get beyond diatomics, it gets kind of complex. But the point that I want to tell you is that an orbital can only hold 2 electrons, but now we can start to spread orbitals over entire molecules is what it is. Pretty interesting, okay? So the next thing here is I'm just showing you guys some different representation of these pi bonds, and just talking about how things are above and below the density. This is just in case you guys need to see it. This is not something different, okay? All I'm telling, or what I'm trying to show here, is sigma bond in between the carbons. Pi bonds are above and below that density there, okay? So I'm just bringing you guys some different examples of how we can draw the pi bonds and the sigma bonds and those kind of things, all right? So if you're having trouble visualizing this, if you don't know what I mean by above and below, that's all that these are here, okay? So that being said, that's pretty much the end of these slides here, okay? The one last point to leave you guys with, all right, is this here, okay? So remember, no matter whether you have a single, a double, or a triple bond, you always have to form a sigma bond first, and then you start to add pi bonds on top of it, okay? But the pi bonds come from unhybridized p orbitals, so you have to have the right number of unhybridized p orbitals to make the right number of pi bonds, all right? And we're not going to deal with this too much, but talking about carbon-carbon rotation and all these kind of things, we'll get to that in organic chemistry, right? So the real important part about these last slides here is just how we can identify the sigma and the pi, right? And that comes from the geometry, it comes from our Lewis structure, and now we can validate that with our MO diagrams, okay? So let's call it homework, I guess. Where is it, right? Your homework would be to practice these examples here and go through those, right? I'll see you guys on Wednesday then.